So good morning to everybody. I'm Metop from Italian Air Force Med Service. I'm the HSAF Precipitation Cluster leader. Today I would speak about the blending technique in general and the use of this kind of technique that we do in HSAF. So precipitation is probably the most important variable in a hydrological budget of the Earth. So the better understanding of the spatial and temporal distribution of precipitation is fundamental for any hydrologic and climatic application. Unfortunately, the homogeneity of temporal and spatial distribution of rainfall combined with the lack of or the sparse presence of ground measurement make the precipitation one of the most difficult parameters to quantify as an input for hydrological model. Meteorological satellite provides a unique opportunity for monitoring the precipitation of a region where ground measurement is limited and consistent with the accuracy of required by hydrology. For this reason, HSAF started as a dedicated satellite application facility dedicated to hydrology. It starts in 2005, so it belongs to the central services of EUMeTrain together with other 7 other SAFs. It was created to provide satellite-derived products from existing and future satellites with sufficient time and space resolution to satisfy the needs of operational hydrology, as I say. And so together with precipitation, we have also products based on soil moisture and snow. It is mandate of HSAF also to have an independent validation cluster. So the products are validated, the usefulness of these products is validated, and so we have all the performance in fighting floods, against floods, landslide, avalanches, and also in evaluating water resources. Well, techniques for estimating precipitation from satellite data exist almost as long as the data have been available. There are techniques for estimating precipitation only based to the cloud top of infrared brightness temperature that is related to cloud top 8 and in the optical peak of clouds. The relationship at the basis of this assumption is that the cloud 8 is related to the cloud thickness. This is an assumption that holds reasonably well for active convective clouds, but is problematic for clouds with a relative warm cloud tops and for example, non-precipitation cirrus clouds. Visible channel, so visible cloud reflectance can be used as a supplementary information for these algorithms to somewhat mitigate the problem. But in the slides you can have you can see an example of algorithm like this is the now casting subconvective rainfall rate. It is based only on geostationary data. Well, microwave instruments have been shown to yield more reliable information concerning instantaneous precipitation rates on account of their ability to penetrate precipitating clouds and interact with its liquid and acid hydrometeors. We had a specific presentation during this week on Monday afternoon. It was made by Giulia Panegrossi. She came in detail of this kind of ability or the microwave instrument to see the precipitation. However, as the microwave instruments are currently only available on board of satellite in low Earth orbit, so only polar satellite, let's say, they do not provide a continuous monitoring of rainfall over a given location. So how can mitigate this kind of lack of data? The first method to avoid or to mitigate the lack of the presence of this satellite is to exploit all the precipitation microwave radiometers available in orbit. And you can see a movie that show how the use of more than one satellite can supply the information about precipitation. You can see with the clock that is running in the bottom right, that every 2 hours and a half you can have the complete coverage of the clock. Or another method to compensate the low temporal resolution is to combine the stationary and low orbit satellite observation. This kind of multi-platform algorithm provides global precipitation estimation merging the high quality sparsely sampled data from low Earth orbit satellites with the continuously sampled data from geostationary satellites. There are several of these kind of blending techniques. One of these kind of merging technique is the CMORPH. This technique was used also in HSAF, but in the course of time we abandoned this technique because it was less operative than the one used in HSAF that I will describe later. So in this case, the CMORPH technique is based on the fact that we need to have 2 precipitation maps. And the geostationary satellite data are used to create a motion vector. So the first precipitation map is moved forward to the second one, and the second one is moved backward to the first one. Then weighted mean is done between the created map, and we can have the precipitation map in between the measured ones. Another blending technique is the one used in HSAF, is the rapid update. It is based on a blended microwave infrared technique that correlates by means of statistical probability matching, brightness temperature measured by the infrared geostationary sensors, and the precipitation microwave estimated precipitation rate at the ground. So in the picture is showed the same cases of the cases that I showed for the convective rainfall rate of now casting up. It is a recent case, the 5th of December of this year, when we had a lot of precipitation, heavy rainfall in the north of Italy. So, how it works? Well, as a new microwave SWOT is available, the microwave-derived pixels are paired in time and space with the coincident geostationary 10.8 microwave channel. And so coincidence data are subsequently located in geographical latitude longitude grid, 2.5 per 2.5 degree in latitude and longitude. And for each box, the histogram between the infrared brightness temperature and the corresponding microwave ray rates is built. So a ray rate is assigned to every infrared pixel, and an instantaneous rain map is produced for with the time and space resolution of this geostationary satellite. And this is a case. The flood event that we had in Grosseto in 2012, here compared between the radar data and the infrared data enhanced picture. So in the course of time, for this blending technique, we tried also to solve a well-known problem, the beam filling problem, because we know about an intrinsic underestimation that we can have. Here an example at the edge of the scan line of the microwave instrument. So the ray rate can come only from a part of the instantaneous field of view that for a microwave instrument could be big, especially at the edge of the water. So the signal is interpreted for all the HIFOV, and we can talk about a systematic underestimation. We try to solve this problem with the use of NEFODINA software. NEFODINA software is an independent algorithm that provides information about the convective cell inside the mesoscale convective system. It is also indicated the phase of this convective cell in development or in decreasing phase. Anyway, the NEFODINA is used, so the scheme is the same, and NEFODINA is used at the beginning of the algorithm and at the end of the algorithm. At the beginning, trying to individuate all the convective area in the scene, and at the end of the algorithm, trying to converge the rain for the pixel really convective. So the rain is redistributed based on the convective area. And this is a case. Here is showed the accumulated precipitation of the previous 3 hours for a case study. In the 1st October of 2009, we had a very strong case in Giampilieri in Sicily, and as you can see, it is showed as after the highlight of precipitation with the NEFODINA, the data are match the reality. So better than before. Currently, the operative products based on this technique are two, the H03 and H15. They are based on the same technique, and H15 is the algorithm that uses also NEFODINA. In particular, the algorithm is fitted only with precipitation estimation from SSMI instrument and MHS instrument. In the near future, this product is already available on the FTP server of HSAF. It's not yet distributed via EUMeTrain because it's still under review, but for the near future, the H03 and H15 will be discontinued, and the floor will be taken by H60. So where the two are combined, so we will have an algorithm that will take as an input all the precipitation microwave estimation available, and with a different treatment of convective clouds, as I explained before. In the far future, the same technique will remain. It will be based on MTG for geostationary satellite data, and together with the other precipitation microwave, we will add the precipitation retrieved from the microwave imager and microwave sounder that will be on board of ADS second generation. Well, looking further in the evolution of HSAF product, we will also have another blending technique for MTG data, and it will be based on artificial intelligence. So this scheme was presented during the AI workshop that we had with EUMeTrain and with other SAFs. As you can see, the algorithm will be based on two modules. The first module will analyze the geostationary data, also using a visible channel to highlight the cloud structure in this preliminary analysis. And then a second module will run with also different, with also two separate run, one coincident with the geostationary acquisition, and the second one with just a few hours later, calibrating with other precipitation microwave estimation. And we are still evaluating the different machine learning approach to be used. As you can see in the slide, we are testing artificial neural network, deep learning, convolutional neural network, algorithm like random forest. We are still in evaluating which kind of this machine learning technique will fit our needs with our data. And that's all. Let me thank all the precipitation team and you for your attention.